In the previous video, we did some simple solubility calculations. In fact, those are right there, at least the ones where we calculated solubility. We didn't calculate K, which are under this piece of paper. And there's a reason that I've hodgepodged this together to look the way it does. We're still going to be doing calculating solubility. We're still going to be looking for S, but now we're going to do it in terms of what is called the common ion effect. All right, the common ion effect is literally when you have some common ion present in the solution with the equilibrium expression. In fact, I'll write some generic words for that, and then we will give it a try. So what we're looking for this common ion effect, it's when we have a situation where some species from the equilibrium system is already present in the solution. And when I say already present, I think that that's kind of a philosophical interpretation. You could do this problem and then add a common ion, and you'd end up in the same place. But you'll see how we set this up, and when I say already present in the solution, I'll put that in quotes. It could be put in there at any point in time. Equilibrium always wins. So how might these problems look when we're spotting one in the wild? Well, it'll be just like this, calculate the solubility given, right? So we're looking at this same thing here, calculate the solubility given a KSP. And so we'll look at example, we did D, E, and F, so this will be example G. And we're going to say again, we've got manganese carbonate, MnCO3 solid, which has a KSP, 8.8 times 10 to the minus 11th, right? So this is where our common ion part comes into play. We'll say 0.10 molar sodium carbonate, Na2CO3. All right? This is how it's different, right? This was our original problem, solubility of manganese carbonate. Now it's solubility of manganese carbonate in something else. Now you've got something present and there's this little bit extra work. All right? Skill number one, or hurdle number one to overcome, is the fact that this sodium ion does not appear in the actual equilibrium expression. So this sodium ion is not part of that, and so I'm not worried about it. It is a spectator there to balance charge. I'm worried about this carbonate ion because it's actually part of my species right there. I'm not worried about the sodium because it's not part of that species that we're going to be looking at. Okay, so we're going to use this same equation. I've got my manganese carbonate. It's a solid. It's going to dissociate, giving us manganese ions and carbonate ions. And our KSP value is still going to be based on our manganese ions and our carbonate ions. And it's still going to be 8.8 times 10 to the minus 11th. All right? All of that should look very familiar because it's exactly the same. In fact, things are going to continue to look exactly the same as I set up my ice problem. And I don't know what kind of trap I want to get into here color-wise. Let's give this a try. We'll set up our ice problem. And we're still not worried about that. That's our solid. It's not involved in the expression. I don't have any of these manganese ions in solution yet. But now I've got some of this carbonate, right? In fact, I have 0.10 molar carbonate, so we have a 0.10 right there, okay? If you've seen the polyprotic acid dissociation problems, those are common ion effect problems when you're doing those calculations. But so this right here supplies some information that now appears right there. Everything else is exactly the same. We're still going to go up by some unknown amount. I'm still going to go up by some unknown amount with one-to-one stoichiometry. This is still going to be S. This is going to be 0.10 plus S now, because we had an amount we started with. So when we plug it in, we're going to get S and 0.10 plus S, and that's going to equal our 8.8 times 10 to the minus 11th. Now there's a shortcut that is very often true, and that shortcut is due to the common ion effect, solubility is going to go down. And if this is a decently sized number, then S isn't really going to change it. So a very, 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 very common mathematical shortcut would be to say that this isn't really S times 0.10 plus S, it's S times 0.1. And then you can just get the answer as 8.8 times 10 to the minus 10th, right? Because S is so small it won't affect the 0.1. We've got calculators that can do this math for us, but like we just did that math in our heads, S in this case equals 8.8 times 10 to the minus 10th molar. Things changed, right? And why did they change? In fact, our solubility here went down, and that solubility went down because we already had a species over here, and that's a pretty sizable concentration. Looking at it from like an energetics perspective, our dissociation happens in that direction. If there's already something over there, it's harder to go in that direction, right? So the idea of common ion effect is it's going to impede the equilibrium from going in that direction, which is how buffers work, by the way. And so your solubility is going to go down if you have a common ion. So we'll say that again in slow-mo. Common ion, already there, makes it harder to go that way. And we saw a pretty significant difference, 4 powers of 10 difference in terms of the solubility. And I'll highlight these maybe in like a different color, because these are our common ion effect problems. Okay. Let's knock these other ones out, and I'm going to save us a bit of time, still totally different video from this video right here. I'll pause this, set these other ones up, and we can plug the numbers in and see how things go. Oh look, there's our aqueous dissociation expression, there's our K equation, and there's our KSP value. All of this is right here, and it's exactly the same. We're still going to do an ice problem, and we're still not worried about the stuff that we have there. And we still don't have any of this, but now we've got some of that silver, and that is 0.35. Let me Ag3PO4, AgNO3. The NO3 is not part of that, but the Ag plus is, and I've got some amount of it right there, which is 0.35 molar. So we have some starting out from some other thing. Or you could pretend that you did this dissociation and then added 0.35 molar silver nitrate equivalent without changing the volume, etc., etc. This is going to go up by 3s. That looks familiar, in fact. Let me switch over to our other blue. 3s. This is going to go up by s. And we end up with 0.35 plus s and s. Looking at this then, we should have 0.35 plus, 3s cubed, and s, which would be 1.8 times 10 to the minus 18th. Again, it's pretty safe to say that 3s isn't going to affect 0.35, so you could chop some work out of that math, but the answer regardless, s is 4.2, 10 to the minus 17th molar. Drastically lower than what we saw here, right? That's a pretty high concentration for us to toss in there, and it was a pretty weak equilibrium system to begin with, and we've got like this factor cubed, so it's even bigger. The 0.35 is cubed. So we get this huge drop in solubility, which is what you would expect in a case like that. And I'll pause while I set up the next one. Spoiler alert, this is going to be exactly the same. Actually, let me write that part out. We're going to do, for example, I, strontium phosphate, just to pull something out of thin air because it's right over there, in KSP, 1 times 10 to the minus 31st, in solution with 0.20 molar, say ammonium phosphate, NH4, 3PO4. A quick note to ourselves, this is our insoluble compound, so I'm not worried about things that aren't part of that. I have strontium and phosphate, I have ammonium and phosphate. Phosphate is the part I actually care about. Had I planned my examples a little better, I maybe would have chosen, with this silver one, something where we had a coefficient that doubled that silver, like, I don't know, an oxalate or something that might be soluble. and then we would have had to double that number here. Like if it had been 0.35 molar Ag2C2O4, then it would have been 0.7 molar Ag plus right there. Maybe we can do that example in another video. I've already lost enough momentum here, so let's just get this written. SR3PO4 2 is our dissociation equation. These are the same every single time. We write our K expression. In this case, that's our strontium ions, but we're cubed, times our phosphate ions squared, and we should have 1 times 10 to the minus 31st. All of that is exactly the same as all of that. Now we just need to set up that ice problem. All of this is the same. I don't have any strontium ions starting out, but I do have some phosphate. I have 0.20 molar right there. And the rest of the ice problem looks exactly the same as it did, plus 3s and plus 2s, exactly like we did. We'll have 3s exactly like we did. And we'll have 0.20 plus 2s right there. And if you've caught on to this trend, that s probably doesn't really matter, but we've got calculators to do it for us. There's really no disadvantage, 3s, except when it doesn't work, because of the math. The numbers get too small and your calculator pukes. But don't consider that unless it comes up. Once again, this could probably be simplified as like 27s cubed times 0.2 squared, so 0.04, but we don't need to do that, right? Calculators can take care of business for us. We end up with a solubility here of 4.5 times 10 to the minus 11th molar, for example, I. All right, when we have this common ion, we end up decreasing solubility because we've already got stuff on the right-hand side of that expression, and so solubility goes down. It's harder to go in that direction. But everything else was the same. All that changed was that little bit of blue stuff, right? This was the same. This was the same. This was the same. Only that little blue piece, right? Here, here, and here versus, well, I should be careful. Here, here, and here. That's all that changed. Once again, same problem. Had a number there. Makes it harder to go in that direction. Our solubility dropped accordingly.